This is Eamonn Ansbro. My colleague Eric Rao and I are looking for unusual technosignatures around the Earth from databases since the 1940s. We have evaluated databases that provide radar, thermal, and visual data where we have performance and reliability in unusual phenomena. We have disregarded all natural and conventional known data that doesn't fit any conventional categories, leaving a phenomena categorized as unidentified aerial phenomena, or UAP. What we have found is extremely interesting that indicates that the UAP negates any known natural state of matter that is the cause, but indicates possible technosignatures around the Earth. This research has prompted the authors to explore a possible monitoring hypotheses around the Earth. However, in order for the hypotheses to be viable, we set up a number of elements to support this proposition. From the background of the research, the authors were aware of the transient nature of UAP has been a scientific problem for scientists to be able to carry out any useful astrophysical research to discover new knowledge. The transient nature of UAP events and unpredictability about when and where the next event will happen is likely one of the main reasons why UAP have not been taken seriously in the scientific community. We propose a hypothesis of a model that may demonstrate potential events happening when a controlled AI-type monitoring of Earth is applied. By using yet undiscovered intersections of orbital tracks at specific locations provides the opportunity of testing the theory at multiple locations favourable for such events to take place. We have discovered a global pattern to UAP events, negating any known natural state of matter that is the cause, with a pattern suggesting that UAP are technosignatures around the Earth, with a discovered orbital period of 66 minutes, and undiscovered inclinations when synchronized with the rotation of the Earth. This global phenomenon required identifying a pattern by systematically collecting reliable data from verified databases on observations from locations with timings. Tools have been used to observe UAP maneuvers from radar, thermal, and visual. We have identified that the global phenomenon of a UAP negates any known natural state of matter that is the cause, and has a pattern that UAP are technosignatures around the Earth. A Python code was developed to find these patterns in UAP data that could suggest repetitive behaviors, clustering tendencies, or periodic movement, drawing potential parallels to pseudo-orbital mechanics in a simplified form. Work is in progress to discover yet intersections of orbital tracks at specific locations at specific times. This will provide the opportunity of testing the theory at multiple locations favourable for such events to take place. Transients have been discovered of artificial objects either in high altitude orbits around the Earth or at high altitudes within the atmosphere. Valorol estimated a projected velocity of approximately 0.5 arcsecond per second. This is significantly slower than the normal angular velocity of an object at GSO at around 15 arcseconds per second. Some transients could potentially be UAP in Earth orbit that, if descending into the atmosphere, have demonstrated high velocity delivery. The Nimitz case is a good example supporting this high-velocity vertical descent delivery of a UAP at sub-seconds duration from high altitude. We carried out an analysis to determine orbital period based on ground observations. A Python code was developed to perform the following: import and pre-process the NuFork databases for analyzing time correlations, search for potential time patterns in the UAP events, such as periodic occurrences, determine orbital parameters, checking whether UAP follow paths similar to known orbital mechanics, such as orbital periods. Geospatial analysis, that's the grouping UAP by location and checking whether they follow a trajectory similar to that of orbiting objects. Cluster analysis, we used DB-scan, that's density-based spatial clustering, to identify clusters of UAP events in geospatial coordinates of latitude and longitude. And trajectory modeling, if the multiple sightings happen in different places at different times, test fitting the data to an orbital period. We also carried out UAP propulsion analysis based on high altitude observations. A GSO object moving at only 0.5 arcsecond per second across the sky cannot be gravitationally bound in a normal orbit. It would need massive continuous thrust to hover there, essentially behaving like a powered spacecraft rather than a satellite on a ballistic trajectory. Based on the assumption above, the UAP needs continuous acceleration upward at 0.22 meters per second squared to avoid falling. This tends to have a spacecraft powered thrust by an equivalent of 160,000 kilowatt hour per day, and more to sustain these orbits. Robert Powell supports our analysis with a case study of a UAP at low altitude, estimating the propulsion power source hovering was also approximately 160,000 kilowatts of power. We also undertook UAP propulsion analysis based on an altitude of 100 kilometers. This required power for a non-ballistic object at 100-kilometer altitude. Its propulsion power requirement and propellant mass flow rate. We speculate that UAP may be on fixed orbital tracks, where the UAP delivers probes on the same orbital track or other orbital tracks where the probes are retrieved. This activity supports a controlled, automated monitoring program. By combining plate-derived angular motion with observer locations on the ground, we can test whether some transient sky events and reported UAP observations are consistent with a common physical source. We have an indication of a UAP pattern around the Earth that suggests a monitoring program may be in operation. Our analysis of UAP at orbital high altitude of 100 kilometers and at GSO provides the parameters for calculating propulsion of the UAP to sustain this constant velocity. Beatrice Vallerot's discovery of objects on a synchronized orbit around the Earth correlates with our finding, showing the evidence of technosignatures of non-ballistic behavior. Our future work will be towards spatial-temporal correlations. We plan the following: use alignment, direction, extent plus exposure time to bound apparent angular motion and test whether it matches GSO-like, HEO-like, or atmospheric scenarios. For each candidate transient window, we will compute where an orbital glint geometry would be visible on Earth and compare with clusters of ground reports at compatible times and locations. We will be prioritizing cases already highlighted as temporarily notable, like the Washington, D.C. 1952 weekends, for focus reconstruction. We'll apply storage filtering and expand vetted samples. Vallerot explicitly noted that better validation and larger searches are the next step. We have listed some references in support of our research.